Assalamu alaikum wa rahmatullahi wa barakatuh. Dear students, in this session I'm discussing normality assumption, one of the classical linear regression model assumptions. In our previous sessions we have covered some other assumptions related to CLRM, but now we are talking about normality assumption. Okay, one thing you should learn, dear students, that the normality assumption is required for a model to be classical, but it's really not required for a model to be blue based linear unbiased estimator. If you remember, we have some conditions in assumptions according to the Gauss-Markov. If they are not met, then the model is not blue. Okay, technically if you have a model, in the model you have beta naught, beta 1 x1, beta 2 x2 in error terms. So these coefficients are estimates we have, right? They are not blue based linear unbiased. In case there are some assumptions by the name of Gauss-Markov assumptions, they are not met. But dear students, in the list of the classical linear regression model assumptions, there are some assumptions which are not required for the model to be blue, and that is the normality assumption. It means the normality assumption is not required for the model to be blue. So you can say in case of the violation of normality, the model can still be based linear unbiased for the estimators. Okay, the question here is then where the normality assumption is required. It's really required in the hypothesis testing, right? Why? Because when we are testing the hypothesis, dear students, we are using the beta 2, beta 3 and these coefficients, right? We just check have these coefficients are the estimates, they are significantly different from 0 using the T statistic and the F statistic, dear students. Okay, so what is the normality assumption? Simply you can say the normality assumption, dear students, that is a situation where the error term in the model, this should be normally distributed. This error term, right, technically you can say the error term that should be distributed normally around the 0 with variance. What do we really mean by this? It means, dear students, if this error term is not normally distributed, this error term, if it is not normally distributed, then the beta 1 and the beta 2, they are just not appropriate for checking the for computing the T statistic value and F statistic value. Why? Because the purpose behind checking the normality just to make sure the beta 1 and the beta 2, they are also normally distributed, or you can say the sampling distributions of the beta 1 and the beta 2 should be normally distributed, right? In hypothesis testing, dear students, we are using the normal distribution. If you remember, we have normal distributions in hypothesis testing. So here we are just putting the beta that equals to 0. So we are just checking that the beta 1 or beta 2, they are just significantly different from the 0. So for this purpose, dear students, the coefficients, the sample distribution of the coefficients must be normally distributed, right? And for checking whether they are normally distributed, dear students, or not, we are just checking the distribution of the normality. So if you found out that the error term is normally distributed, right? If this error term, dear students, this is normally distributed, then you can say the coefficients we have, that is also normally distributed. You can say the beta 1 head that is normally distributed, right, with the mean value of beta 1 and the variance of beta 1 head, dear students. Okay, so this is the technical way. It means if the error term is normally distributed, dear students, then you can claim that yes, the coefficients, they are also normally distributed. Okay, once again, I'm just quickly repeating, dear students, the purpose behind the normality, dear students, the only focus is just that the error term should be normally distributed. Okay, this means the error are symmetrically distributed around 0. This is what I've just explained. The error, if the error is just normally distributed like this, you can see it's symmetrical around the 0. This is bell-shaped curve, right? So it means the error is having the bell-shaped curve. Most values close to the mean value, few they are at extreme in this way. Some few value they are at extreme. Okay, simply, dear students, if you have the model, So in our model, the error term should be normally distributed. If it is not normally distributed, it means the normality assumption violated. In that situation, you can say the T statistic and the F statistic, they are not valid, so the hypothesis testing is just not correct. Okay, next is why do we need the normality? They have just explained normality of error is not needed for OLS to be blue, but it is required for valid inference, right? Okay, when we are just inferring our result and generalizing, right, to the whole population, we are using the T statistic and F statistic. And this T statistic and F statistic, these values, these tests, they are based on the sampling distributions of the coefficients, right? The beta 1 and beta 2, and for that we are using the normal distributions. So that's why you can say if the error term that is not normal distributed, then the T test and the F test in the confidence interval, they are not just correct. Okay, dear students. Okay, in short, we say we need normality of errors to ensure beta hat, which is the coefficient, should be normally distributed, right? Okay, the technical explanation, dear students, you can say if the error term is normally distributed, then you can say the beta j, which can be beta 1, beta 2, beta 3 head, they are also distributed normally with the population counterpart beta j, right, and the variance beta j head, right? So this is the technical way. If the error term is normally distributed, then you can say the coefficients, they are also normally distributed to yourselves. Okay, one point I just try to make sure here, right? It is in the model research we are talking about the dependent variable, right? You know, 1x1 and beta 2x2 and error term. So the error is just part of the y resonance. When we are predicting the y, so there is the possibility that the error in the y resonance that is just not normally distributed. So once that is just not normally distributed, then you can say the beta 1 is not predicting the changes in the y in an appropriate manner. So that's why this is the logic behind. So you can say the normality of the y is really required. If the y is normally distributed, so you can say the error term is also normally distributed, most probably. So that's the condition for the normality response. Okay. Okay, each individual coefficient is centered at the true value when we are talking about the normal distribution has a variance we can compute. Okay, this allows us to perform t-test and the confidence interval. Okay, next we have what happens if normality is violated. In case of normality, OLS estimates are still blue. This is how I've just repeated. You can say the ordinary least square method is best, linear, unbiased, but the T and the F test, they are not valid. The confidence interval, which is based on the T statistic value, right, that is also not reliable. Okay, results may be misleading, especially in small sample. Okay, this is important. If this sample is small, then you know that the population or the data sets or the observations we may have may not be normally distributed. But if the sample is large, according to the central limit theorem, we can say that yes, the data is just normally distributed, right? It helps approximate normality. What do we really mean by that? It means if the data is just getting, if the sample size is getting larger and larger, then the data sets are, you can say, the observations that tend to be normally distributed, simply you can say. Okay, it means the y, when you collect the data and y and the sample size is really large, then the y tend to be normally distributed, and this is the claim of the central limit theorem, and this is something true. When the sample size is really big, then the data is normally distributed, but the sample size is, when it's less, then there is a concern whether it's normally distributed or not, right? Okay, so the issue in case of large sample, that is just we are not worried about. Okay, next, how to check normality of residuals. We are using different method. We are using the histogram method. Inshallah, I'm just teaching in Strata. We are using the QQ plot method, and there a method, the Jark Baratis, right? And also one more method which is missing here. Let me just include it. That is the, we have, okay, the number 2. we have SK test. This is a method for checking the kurtosis and skewness, right? Okay, this is number, so this is 4, and here this is 5. So these are different method. We are using histogram of residual QQ plot method. This is just graphical method. Shall I learn in the scatters method? And we have the Jark-Barrett test, Shapiro-Wick test, right, for small samples. So in case of the Shapiro-Wick test, the p-value is less than 0.05, or in case of the SK test or whatever test, if the p-value is less than 0.05, then we reject normality. We may suspect there is normality resistance. Okay. Okay. Next, what are the solutions, the method, inshallah? These are some different solutions. If there is normality, how we can solve the normality. Now we're just going to Stera, and I'm teaching you how you can detect the normality. Okay, dear students, just click on the file, and I'm importing my file from Excel spreadsheet, and click on browse, and I have a special file by the name of normality, right, for Stera. Okay, here I have a dataset, dear students. In this dataset, my dependent variable is performance, and I have 3 independent variables: educational level, salary, and experience, right? Okay, I'm just dropping. Why? Because this is a categorical variable, so that's why right now I'm dropping this. Okay, we have 2 numerical independent variables which are not categorical, such as salary and experience, and performance is our dependent variable. For checking this relationship, dear students, we are just running the regression. Reg dependent variables performance. We have 2 independent variables. Now, the if statistic value is less than 0.05, so the MAR is significant overall. Other 2 independent variables, salary and experience, they are also affecting the performance positively. One is positive significant and another is negative significant. You can say the salary and the performance, they are positively correlated, right? There is a positive relationship, and the experience is affecting the performance negatively. Okay, in this situation, in our dataset, maybe logically this is not true. Why? Because with more experience, the performance should get better. But this is just a hypothetical situation I'm just explaining. Experience is having a negative coefficient, which means the higher for every extra year of experience, the performance is just decreasing, right? Or you can say when employees get older with more experience are less likely to have higher performance, but not necessarily true, but generally you can say experience is positively correlated with performance, but in our situation it's negative, right? Okay, so before I'm considering this output, dear students, I should check for the normality. So you should predict the residual, right? Why the residual normality is important, and you should write resid. Okay, now we have one more independent variable, residual, and here you should type. We have a command. We have many methods for checking the normality results, but I'm just using this method, SK test method, right? So SK test and type residual. Okay, now according to the SK test, the p-value is less than more than 0.05, so you can say the data is normally distributed. Why? Because we are failing to reject the null hypothesis. And what's the null hypothesis? The data is normally distributed. So keep in mind the favorable value resolution is if the p-value is greater than 0.05. Okay. And similarly, the p-value of the skewness and kurtosis. This is also okay. What's the skewness and kurtosis? Okay, let me just show you. If you have normal distributions, so with the normal distributions, we assume that the error should be just looking like this. It should be normally distributed like this. Okay, so if this is the central value, so it is symmetrical, right? It's mean this half just looks like exactly another half, and you can say the skewness is also symmetrical, and there is no more skewness in one side. So if the graph is just like this, you can say the graph is skewed to the right, for example. if the graph is just like this, you can say the graph is skewed to the left, right, in this situation. So in normality assumptions, we assume there should be the symmetrical shape. It means the skewness there shouldn't be skewness in either side, either in the right or on the left side.